Hi, I'm Alan from the High-Speed Signal Path Applications Group at National Semiconductor. In this video, I'll be discussing and demonstrating the LMK04800's new feature called Holdover Mode. The LMK04800 is a high-performance, highly configurable jitter cleaning clock generator for wireless infrastructure and other high-performance applications. One of the key applications of this device is shown in this system block diagram, where the LMK04800 is providing multiple clocks within a wireless base station radio unit. Here, the LMK04800 is providing these clocks to drive ADCs, PLLs, DACs, and other high-performance blocks within the radio unit. And the LMK04800 must be able to synchronize its output clocks to the reference. Here, the reference is provided by the SCAN25100 SerDes, which receives a CPRI signal from the baseband unit in order to synchronize the remote radio head. The LMK04800 must provide reliable operation when the reference clock is lost and also when it's later restored. In order to maintain reliable operations, the LMK04800 must operate seamlessly without excessive output frequency drift and without degraded jitter and phase noise performance. Here we can see the internal architecture of the LMK04800. In order to minimize frequency drift on loss of reference and improve system reliability, the LMK04800 provides a holdover function. There are two holdover modes that can be programmed, and also the ability to disable holdover mode if desired. The first programmable holdover mode is called tracking mode, in which the LMK04800 monitors the V-tune voltage on the VCXO when the PLL is locked. When the PLL lock is lost, the holdover will hold the last tuning voltage to within plus or minus 6 millivolts, which is the tracking error of the internal DAC. Over here we can see the holdover accuracy equation, which depends on the tuning voltage, tuning sensitivity of the VCXO, as well as the VCXO frequency. And that's how you can calculate the holdover accuracy in terms of part per million. The second holdover mode is called fixed mode, where the user can set the tuning voltage anywhere between 0 to 3.3 volts with about 3.2 millivolts of resolution. If desired, holdover can be disabled, and in that case, the charge pump output would be tri-stated and the tuning voltage would drift. In that case, the frequency accuracy is limited by the absolute pull range of the external VCXO. In this slide, we can see that the various holdover capabilities provided by the LMK04800. On the left side, we have 3 activation methods, which are the different ways that the LMK04800 can enter holdover. And for each of those activation methods, we have separate columns which indicate the ability to enter the 2 different holdover modes from that corresponding activation method. As you can see, it doesn't work well when your activation method is the oscillator tuning voltage drift method to use tracking mode. So in this mode, it's recommended to use fixed holdover mode for this particular activation method. In this demonstration, I will use the PLL1 loss of lock as the activation method to enter tracking mode. This provides a very good holdover accuracy, and right now I'll be able to demonstrate that. Here we have the LMK04800 evaluation board. We're receiving a 122.88 megahertz reference clock from our signal generator, which sets the frequency accuracy of the output clocks generated by the LMK04800. As you can see, the lock detect LED is shown, which means that our PLL is operating normally and locked to the reference. Here we have 2 outputs that are generating 122.88 megahertz, which are both locked to the reference. The first output is being fed to our frequency counter for measuring the frequency accuracy, and here we can see that we're exactly 122.88 megahertz. On the second output clock, we're measuring the phase noise performance of the LMK04800 outputs. So you can see over here that the 122.88 megahertz output is measuring about 128 femtoseconds of RMS jitter over an integration bandwidth of 1 kilohertz to 20 megahertz. When we're locked, we can see that we're also measuring the tuning voltage when the PLL is locked. Currently, the voltage is about 1.672 volts, which is holding steady. To demonstrate the holdover mode with the in tracking mode, we can now remove the reference and we now see that the holdover LED is lit, indicating that we're operating in holdover mode, and the green LED is off, indicating that we've lost lock. So we can see that the frequency accuracy has not significantly drifted. We're only about 13 hertz off from our center frequency of 122.88. And down here we can see that our tuning voltage hasn't drifted either. We're only about a couple millivolts off from the previous locked voltage. Over here, we can look at the phase noise, and we can see that the RMS jitter over the 1K to 20 megahertz bandwidth is 135 femtoseconds or so. So we haven't significantly degraded the phase noise and jitter performance from the previous lock condition. So in order to demonstrate the ability of the LMK04800 to automatically relock, we can provide our reference signal back and verify that the LMK04800 can automatically exit holdover mode when the phases of the output clock and input clock are realigned. So as you can see, the LED has now lit up, and we're now indicating normal PLL operation, and that's verified over here on our frequency counter, where we're now measuring about 122.88 megahertz. So as I've demonstrated, the LMK04800 provides very reliable output clocks with minimal frequency drift and excellent phase noise performance in holdover mode. For more information, please visit national.com/timing, and thank you for watching.